Today we're going to talk about a property in isosceles triangles, which is very handy. So I have a isosceles triangle ABC, all right? AB equal AC. And then there is a random point D on BC. Then we have this result. AB squared minus AD squared equal DB times DC. It's actually very easy to remember. Think about DB times DC, all right? It's coming from D, right? The two segments, DB times DC. Now, there are probably many ways to prove it. Maybe something more like Stewart's theorem or something more advanced or something fundamental as law of cosine. But we could try even a simpler proof, which is probably you just draw a height. All right, call this point H. You draw a height from A onto BC. Because this is an isosceles triangle, when you draw a height, you then have BH equals CH, right? Now, AB squared equal AH squared plus BH squared. AD squared equal AH squared plus DH squared, right? Pythagorean theorem, everybody knows. All right, we are ready to do a subtraction. AB squared minus AD squared. So this AH squared components cancel, right? So it's BH squared minus DH squared. That is BH minus DH times BH plus DH. What is that equal to? BH minus DH. So this one minus this one, what you have left is DB, right? Times BH plus DH. BH plus DH. Okay, let's leave this DH. But this BH is the same as CH, right? BH equals CH, right? So this component is actually DC. And that's it. This is it. That's the proof of this little result. Okay, very easy to remember. Now, this point D is moving on BC, right? If point D is at some extreme position, such as D, is at point B, if D moves closer to B, for example, all right, D becomes B, D stands on B, what happened? Well, left-hand side is 0, right? AB squared minus AD squared becomes 0. On the right-hand side, DB is 0. That makes sense, no? Both sides are 0. If D becomes the midpoint of BC, the point H, what happens? AB squared minus AD squared, that becomes, the left-hand side becomes what? BH squared, right? BH squared is what? DB times DC. Now, when D is at the midpoint, makes sense, right? It's HB times HC, which is DB times DC, when D is standing at point H, right? Okay, what about point D moving out of BC? Actually, the theorem does not change. Let's take a look. If you have this point D on the extension of BC, on one side of it, all right? It's not within, but beyond that, beyond BC. The theorem does not change. AD squared minus AB squared equal DB times DC. All right, the right-hand side is still the product of two segments that both coming out of D, all right, DB times DC. And to prove it, we're gonna apply the same simple approach. You draw a height, AD squared equals AH squared plus DH squared. AB squared equal AH squared plus BH squared. Nothing has changed, still Pythagorean, right? Now we do the subtraction. AD squared minus AB squared equal, again, AH components, this AH squared is canceled, right? DH squared minus BH squared. That is DH minus BH times DH plus BH. Let's see, DH minus BH, DH minus this, that is DB, right? Times DH plus BH. But remember, this BH component equals CH, right? So DH plus CH, which is then DC. And very interesting, the formula didn't really change much. If you take a look at the previous one, AB squared minus AD squared, that's obvious. Right? When D is inside, AD is less than AB. The difference of the square is DB times DC. Now, when D is beyond BC, the right-hand side of the formula did not change. The left-hand side just, you move the bigger one in front, right? You're gonna keep it positive, AD squared minus AB squared. So what do we do with this? Let's see something in action, a problem in AMC 10 a couple of years ago. Problem 23, let's read the question, okay? Triangle ABC, AB equal 86. AC equal a little bit longer, 97. AB 86, AC is 97. There's a circle with center A. Radius is AB, so there the circle goes like, maybe like this, passing through B, right? Something like this. Intersects BC at point B and X. Telling us that this is an integer, this is also an integer. What's the length of BC? Well, we don't have a isosceles triangle, or do we? We do, right? Now, I'm not gonna keep the circle here because I think if we apply the little theorem that we just learned, the circle is irrelevant, because if you simply connect AX, this is 86, right? Because it's part of the circle and AB was the radius. So AX is also the radius, AX equal AB. So that triangle ABX is isosceles, right? What's the theorem again? The theorem says AC squared minus AX squared equal CX times CB, right? In 5 seconds, you can write down this. Now what's next? 97 squared minus 86 squared equals CX times CB. And that is 97 minus 86. You're not gonna really calculate the square, right? You're gonna use the difference of square formula. CX is integer, right? CB is also integer, okay, right? It's the sum of two integers. So this is 11. This, if you take a quicker look, it's 3 times 61. 183, right? That equals CX times CB. All right, so now you're gonna think, some integer times another integer, you call the product of 3 prime numbers. I have a couple of choices here. Maybe, CX looks kind of small here. Maybe it's 11, maybe it's 3. Could it be? Could casework now, you think. CX is 3, 11, maybe 33, maybe, 3 times 61, 183. I mean, all that kind of choices are coming up. But take a closer look. CX is part of this triangle. There's a 97, there's an 86. So CX what? CX is at least 11, right? Because 2 sides longer than the third, right? The sum of 2 sides longer than the third one. So CX cannot be 3. CX cannot be 11. Makes sense to say CX is 33. Right here. Can CX be 61? You say, why not? Well, if CX is 61, then CB is 33. It doesn't make sense now because CX needs to be less than CB, right? Look at the graph. No, CX is shorter than CB. So, okay, I think we can settle right here, right? CX equals 33, CB equals 61. Let's go. That's it, right? We didn't really use anything about the circle. There is a big circle right here, looming in the back, right? We didn't really look into it. We only used the fact that this AX is 86. And that's all we need to do for this problem. But it does bring up an interesting subject I want to talk about, which is, if you look at this formula, dB times dC. Now, this is a very important type of pattern in geometry. A product of 2 segments, one is slightly longer than the other. dB times dC. This should remind us something to do with a circle, because if you have a circle and there is something called power of a point. Suppose a circle got cut by this line at point B and C, all right? D is a point outside. Then dB times dC equal something. What is that something? It's the square of a tangent segment, right? Suppose dp is a tangent, then it equals dp squared. Power of a point, right? Okay, so this is something that we should think about. Well, there is no circle that's here. Well, at least not clearly where the circle. I don't know where. Is there a circle? Does this have anything to do with the circle at all? Think about it. Think about it. Maybe we could connect some dots. All right. Think about it, and we'll talk about it next time. All right. We could add a circle and to sort of connect the dots to connect this formula to power points. I want you to think about it, and we talk about it next time. Okay.